Hello and welcome to the lesson 9-3 practice. As you know, I don't typically do videos for the practices, but if maybe working the practice through a video can help you understand it a little bit better, here we go. So item 20, we're using this arrow that they've given to us on the coordinate plane, and it says, draw the reflection of the arrow described by each of these functions and identify the line of reflection. So we're going to do those two things, draw the reflection and identify the line of reflection. So on A, they tell us that the function is eight minus x comma y. So I'm using a function table here for A. Not necessarily that you have to do that. And if I can explain what this function is really telling us to do, maybe a function table is not needed at all. So there's really no rhyme or reason why I choose certain points on our pre-image, other than I think these vertices will be the easiest to draw our image using. So this first point, the tip of the arrow, is located at 0, 3. This top corner here is located at 2, 4. The bottom corner of this arrow is located at 2, 2. And this back corner, or this back edge, is located at 4, 3. Notice I didn't use the other two vertices because those are at halves. Again, it's all points on this pre-image that are getting reflected. So I'm just going to use 4, 3. So this function tells you to take 8, subtract your x, and keep y the same. So if 0 is our x for our first coordinate, 8 take away 0 is 8, and keep y the same, which will be 3. The second coordinate, x is 2, so 8 take away 2, our x, will be 6, and keep y the same. Same thing here, x is 2, 8 take away 2, our x, will be 6, and keep y the same. And last, 8 take away 4 will be 4, keep y the same. Now there is a special reason that this point will not go anywhere. We're learning, hopefully in our lesson, that points on the line of reflection do not move. It's because however far a point is from the line of reflection, that's how far it travels. So for us to see that 4, 3 goes to 4, 3, we should already tell, or should be able to tell, that the line of reflection is through x equals 4. But maybe you can't see that, so let's graph these points. So 8, 3 is the tip of our arrow, 6, 4, 6, 2, and then 4, 3. So let's establish what this function is really telling us. So when we see 8 minus x comma y, we're actually seeing a reflection across the y-axis. I'll tell you why I know that. Because the function for a reflection across the y-axis is xy goes to negative x comma y. This is a reflection across the x-axis, or excuse me, the y-axis. It's a reflection across the y-axis when the x changes. So look at the function. Really, we're adding 8. It's a positive 8, but it's a negative x comma y. So this is a reflection across the x-axis, or y-axis, excuse me, I keep mixing those up. A reflection across the y-axis, and then translated to the right, 8. So our arrow should actually point this direction. Well, we know a reflection is a rigid motion, so this image should look pretty close to our pre-image. And hopefully we can find the line of reflection. One of the best ways to do it is by connecting corresponding points, and then finding the distance halfway. So if I connect this vertice to this vertice, which are corresponding points, or the tip to the tip, halfway between those 2 points is my line of reflection. So the line of reflection for item A should be x equals 4. Now let's move on to B. I'll use another color for B. B tells us negative 2 minus x comma y, so we're going to create another function table. Negative 2 minus x comma y. So we're going to use the same pre-image points here. So 0, 3, 2, 4, 2, 2, and 4, 3. Now we're using this new function. So it tells us to take -2 and subtract x. So -2 minus 0 will be -2 still. Keep y the same. So it'll be -2, 3. 2, 4, that tells me to take -2 and subtract 2. So it'll be located at -4. Again, keep y the same, which is at 4, not 3, looking at the other coordinate. Again, -2 take away 2 will be -4, keep y the same. And last, -2 take away 4 is -6, keep y the same. So notice we don't have a point that remained in its same location, so maybe the line of reflection is not going to be as obvious. So let's graph these new image points. -2, 3 is located here. -4, 4 is located here. -4, 2. And this point here. Now, if you're wondering how to finish or draw this arrow, let's look back at the function again. Notice it's -2 this time instead of +8, but it's still -x comma y, which is still a reflection across the y-axis. So this arrow flips across the y-axis and then backs up 2 units. That's what the -2 does. So our arrow should actually be pointing the opposite direction of the pre-image. So now if you're wanting to find the line of reflection, maybe it's not as obvious, but connect your 2 tips of your arrow and then take half that distance. Because however far a point is from the line of reflection, its image has to be the same distance. So these two, when I look at the distance between corresponding points, I should be able to split that distance in half and find the line of reflection, which in this case is at the line x equals -1. So the line of reflection for item B is x equals -1. Now let's move on to item C. I'll use another color for that, maybe red on this one. Now this function's a little bit easier. This function is actually the function for a reflection across the x-axis. Notice the x stays the same, but the y changes. So a reflection where the x stays the same, but the y changes signs is a reflection across the x-axis. So we're going to take this pre-image and reflect it across the x-axis. I'm actually not going to use a function table here, and I'm going to use the basic understanding of what a reflection does. So the tip of my arrow is located at 0, 3. So however far that point is from the line of reflection, the x-axis now, that's how far I have to go on the other side. So now 0, 3 will be located at 0, -3. Same thing for this top point on the arrow. This is located at 2, 4, 4 units from the x-axis. So I now need to travel 4 units down across the x-axis, which will be located at 2, -4. Likewise, with this point located at 2, 2, I'm going to go down 2 units to the x-axis, then go 2 more. And so I can finish out my arrow, a reflection across the x-axis. So if you can see, that pre-image flipped across the x-axis to end up here, the image. They still want us to know the line of reflection. So you could either refer to this as the x-axis, or like these last two, there is an equation for a line that passes through the x-axis. Well, if x equals some number is a vertical line, what do you suppose a horizontal line is? Well, x changes all day long. Left, we get negatives. We go right, we get positives. But y is a constant number on this line. In fact, y is 0 on that line. So we could either say the x-axis or the line y equals 0. Now, that's completing these reflections according to functions. Now let's transition into item 21. This is a very important question, very important. I'll even put 3 stars just to show it's important. It says, describe a reflection that would map the arrow onto itself. What they're asking here going back to this pre-image error, the first one that they gave us, what reflection could we use so that the arrow appeared to have not gone anywhere? In order for this to happen, we have to have some kind of line of symmetry. That's what has to happen. In order for this arrow to appear to have not gone anywhere, still abiding by some reflection, there has to be a line of symmetry. So, find that line of symmetry. Well, it might be best to turn your head, but hopefully you can find that there is a line of symmetry. And I'll kind of change the color a little bit here. There is a line of symmetry that cuts this arrow, or in fact, all of these arrows, in half. In other words, this top corner would reflect over this line and end up here, and this bottom corner would reflect over this line and end up here. The tip of the arrow would stay in its same location because points on the line of reflection do not move. So if I were to reflect this pre-image over this line of reflection, it would map onto itself, or map in its same location, or move in its same location. So the question is, what is the equation of this line that I just drew? Well, a horizontal line is y equals some number, like we saw with the x-axis, it's y equals 0. So what does y equal at every single coordinate on this line? Well, y equals 3. So we could say that a reflection over the line, or across the line, y equals 3 would map the arrow onto itself. But it really all depends on this concept here, a line of symmetry, which brings us to item 22 through 24. It says irregular pentagon. Hopefully you learned in the previous lessons, regular pentagon means all sides are congruent and all angles are congruent. So irregular means not all sides congruent. And I'll go and say not all sides or angles congruent. So a regular pentagon means all sides, all 5 sides, all 5 angles are the same measure, but irregular simply means not all sides and angles congruent. So irregular pentagon ABCD has exactly one line of symmetry, which passes through point A. 22 says, what is the image of point C under reflection across the line of symmetry? Image is not a picture anymore. Image in the context of geometry means where does that point locate after the transformation? So if this really is a line of symmetry, as they're telling us, then this side that contains ABC should map across that line to the side with AED. So imagine if it were to reflect over that line, B would map to point E, A would map to itself, and C, the image of point C, would be, boom, point D. Hopefully that makes a little bit more sense now that I've explained it. And so we actually already mentioned item 23. Does any point remain fixed? That means does not move or maps to itself, if you will, under reflection across the line of symmetry. Explain. Well, point A, because it is on the line of reflection, will not move. So point A, and they ask us to explain, so please do that. Points on the line of reflection, or in this case, symmetry, do not move. Or in other words, they map onto itself. Because really, all points in a figure have to obey the reflection. The reason they appear to not move is because in a reflection, however far a point is from the line of reflection, that's how far it has to travel. So E, let's say for example, E is an inch away from the line of reflection. After it reflects, it has to travel an inch on the other side. That's why it maps to point B. So if A is on the line of reflection, it technically has a distance of 0 to the line of reflection. Well, the reflection told it to reflect And so it tried to travel a zero distance. That's why it appears to map onto itself. And 24 really should have been asked a little bit earlier. It says which sides of the pentagon must be congruent. In order for a pentagon or hexagon or triangle or square, any kind of polygon, to have a line of symmetry, sides have to be congruent. Really what we're saying, if there is a line of symmetry, then I could fold this pentagon on this line, and this half over here with these points A, E, D would fit perfectly on top of A, B, C, suggesting that there are sides congruent. So if E maps to B, then line segment AE has to be congruent to line segment AB, because point E maps to point B. And likewise, if point D maps to C, then line segment ED has to be congruent to line segment BC. For that very reason, E maps to B and D maps to C, if this really is a line of symmetry. So I hope that explanation helped as we explore reflections and reflectional symmetry. Thank y'all for watching.